is one important factor, and he has considered the structures involved in different aspects of reward-based learning, social reward, and in doing so he has used not only humans but also other primates and even rodents, and a multitude of experimental approaches, and obviously been very successful in this endeavor. So may I now call on you to deliver your Caddy lecture on reward-guided learning and decision-making in the frontal lobe.
Okay, thank you very much for the invitation to speak here. It's a great honour to be speaking at Fens, especially here in Barcelona. So my talk today is about these 4 regions of the frontal cortex. And if you pick up any copy of the neuroscience journal that's published this month, I'm sure there's bound to be an article in there somewhere talking about at least one of these areas and arguing that it has some role in some aspect of reward-related decision-making and learning. And I'm going to be trying to put forward a set of hypotheses about the different roles that these areas have in decision-making and in learning. So it's the case that they sometimes work together, there are interconnections between them, but all of them also have unique connections that mean that they're in receipt of different types of information to one another and in positions to influence the operation of different parts of the brain to one another. So what I'm going to be focusing on then are 2 themes. Decision-making is the first one, and here the idea is that ultimately what guides the choices that we make in many situations are the expectations that we have about what's going to ensue afterwards. So the idea is that we're often making choices about what we think is going to lead to the greatest amount of reward. So I'm going to be looking at very simple type of situations where sometimes animals or sometimes humans are choosing between different amounts of reward. Normally the choices aren't being made between the reward items themselves, but between stimuli that have some type of association with those rewards. So in some situations, different stimuli might be associated with greater or lesser amounts of reward. In other situations, the associations might be of different strengths. So it might be, for example, in this case, we've got one item that has a high probability of reward, another one that has a much lower probability of reward. And in order to work out what's the best one of these 3 stimuli to pick, you need to bear in mind both these probabilistic associations and the different reward magnitudes that are associated with these different stimuli. Now the second part of my talk is going to be about learning, about how we revise our expectations about how good a choice might be with experience. So for example, if we repeatedly have the opportunity to make the same choice again and again, then we might experience slightly different outcomes. We might begin to revise upwards our expectations of reward in association with a certain stimulus, if choosing it repeatedly delivers reward. And one of the ideas that I'm going to be referring to here is to the idea of prediction error learning. So this is going to be the only equation in my talk today, and it's a very simple one. The idea here is that every time that we make a choice, we have an expectation or a prediction about how good it's going to be. So in this axis here, we can imagine that we're plotting the value of our expectation, our prediction, and that's indicated by this term in the equation here. Then we make the choice, we receive an actual outcome for making the choice, and it's either better or worse than our expectations would be. So in this case, it's better. So what we have is a discrepancy or a prediction error between the actual outcome we receive and our prior expectation. And this term is up here in this equation again. And what it's telling us is that our next expectation on the next trial, the next time we make a choice, the value expectation on trial t plus 1 is going to be a function of our previous value expectation plus some function of this discrepancy or this prediction error. Now these prediction errors, there's some seminal work of Schultz, Diane and Montague. These prediction errors have been associated with the dopaminergic system and with dopamineceptive regions such as the striatum. But I'm going to be arguing that sometimes the frontal lobe the areas that I'm going to tell you about also have an important role to play in using prediction errors in order to update and change behaviour. Okay, so the first thing then that I'm going to turn to is the one of decision making. And I'm going to focus on just one of these areas, and it's this one here, the ventromedial prefrontal cortex and the medial orbitofrontal cortex. So these are two adjacent structures just around here. I'm sure there are differences between them, but for the purposes of this talk, I'm going to treat these two areas as the same. And I'm going to start off with an fMRI experiment that was conducted a few years ago by Erie Borman, a graduate student in Oxford. Now, the idea of this experiment is to look at how we compare the values of different possible choices in order to come to a decision about what's the best thing to do. And this experiment was conducted with human subjects in an MRI scanner, and they were looking at a screen that looked a bit like this. So they have two choices on the screen. They can either pick the left-hand option or the right-hand option. And both of these options are associated with different numbers of points that are indicated to the subject on the screen. So in this case, you might think that the obvious choice to make is the right-hand choice because it's associated with 55 points. And if you get those points, that's ultimately going to be translated into a greater monetary sum at the end of the experiment. But the catch is that these stimuli only have a certain probabilistic association with reward. And I've plotted those on the graph at the top there. What you can see in purple is the probability of reward associated with the left-hand option, and in black with the right-hand option. So if we take a typical trial, let's say the 40-second trial, I think this is, that I've highlighted with the red circle here, what you can see is that the left-hand option has a higher probability of reward, but here on the screen you can see that it's got the lower magnitude of reward that's associated with it. So to pick the best choice, you need to combine probability and magnitude in order to work out that the right-hand option is the best one to take. Now what we can then do is we can then look at the difference in the value between the option that's chosen and the option that's rejected on every one of the 120 or so trials of the experiment. And we can construct a series of numbers which is the relative value difference between the chosen and the unchosen option on every trial of the experiment. And we can then use this as a regressor to interrogate our brain activity. So in other words, what we're doing with this, what we're going to do with these series of numbers, is we're going to look for a brain region where the activity is going up and down in tandem with this relative chosen value signal here, with this very relative chosen value number. And if we do that, we find there's one place here in the ventromedial prefrontal cortex where the bold signal is covariant with the relative chosen value between what you've chosen and what you've rejected. We can unpack it a little bit like this. We can see that what I'm showing you here is not the bold signal itself, but the regression coefficients relating the bold signal to that relative value difference between the chosen and unchosen options. And what you can see is that it's peaking around about the time that a choice is made, so given the hemodynamic lag, that probably indicates that it's indexing something that occurred at around about the time that the subjects were making their decisions. We can unpack it even further into two different parts. A positive relationship between the bold signal and the value of the option that's chosen, and a negative relationship between the bold signal and the value of the option that's rejected. So one interpretation of this is that this actually constitutes the decision process, the process of choosing between these two different options. Here we've got the representation of the option that's ultimately chosen coming to dominate the bold signal. And here we've got the representation of the option that's going to be rejected, gradually having a more and more diminished impact on the bold signal. So that's one interpretation of the data. And in order to try and test it, what we've done is to look at the effect of lesions in this brain region in macaques. So what you can see here on the top right of the slide, shown in red, is an overlap summary of the lesions in 4 macaques. And the task that we tested them on was rather similar to the one that we gave to our human subjects. So they're going to be choosing between stimuli. Now they're stimuli of different shapes that are associated with different rewards. The rewards are always the same in association with each of the stimuli, but the probabilities of the associations are going to vary. And every day that the macaques come into the lab, we're going to give them 3 new stimuli to learn about. And there are going to be 3 sets of trials, and they're going to enable us, I hope, to look at how value comparisons are being made. So here's one set of trials that the animals encounter. So there might be one stimulus with a high probability of reward, a 0.6 probability of reward, and the 2 other stimuli have a very low, 0 probability of reward. And the idea behind these types of trials is that it's very easy to work out what's the best thing to choose, because only one of the options has any association with reward. Now, on other days, which are tested with new sets of stimuli, one of these ones of the worser options here might have some association with reward. So the idea is that now it's slightly more difficult to discriminate between the best and the second best option. In the third set of trials, again with new sets of stimuli, this process of comparison between the best and the second best option gets even harder still. So now this probability is beginning to approach that of the best of the options. So the thinking is that if this ventromedial region is really critical for how value comparisons are made, then the lesion is going to particularly impair the animal's performance on making these most difficult of value comparison judgments when the best and the second best items are close together in value. So here are the results. What you can see are preoperative data in green and post-operative data in blue. And on the y-axis I've plotted the number of times that the animals are choosing the best of these 3 options. And across this axis here, we've got trials across a session, and these have been averaged over several days. And what you can see is that post-operatively, the animals are not really significantly worse than they were pre-operatively. But these are the trials where the best option is clearly different from the worst options. However, in other sets of trials, over here, for example, we've got the second best option approaching the value of the best of the options. And now we can see the post-operative performance in blue is significantly worse than the pre-operative performance. The animals are significantly impaired when the value comparison demands are higher. Here's another way of showing a deficit in the way in which they make comparisons between the values of choices. If you focus on the left-hand side of this figure, first of all, what you can see on the y-axis there is the number of times that animals are choosing option X rather than option Y when they're being allowed to compare option X and Y together. And as we go across the X-axis,